You may have guessed from my name that I'm British. And I was British and just British until one day after Brexit vote, the referendum. And then I applied for German citizenship, and now I'm German and British. I was reading the other day that being British puts me in the unique and enviable situation belonging to a country, a nationality, which is the first country on Earth, the first quantum country on Earth. So it's both, and it's in superposition. So we are both in and not in the European Union. As you can, which is incredibly embarrassing. As you can see, I'm a camper. Amazing tent. Anyway. So I'm going to talk to you about quantum computing, and if I take too long, somebody here at the front is going to come up on stage and beat me up. My Dutch is non-existent, und wenn ich anfange Deutsch zu sprechen, please correct me, it's just unavoidable. I've been living there for 30 years. System Q on the right there, I'll talk about that as well a bit at the end. But just to get started, I too have a picture of lots of physicists. This isn't the Solvay conference from 1927, where quantum mechanics kind of got created. This is the MIT conference from 1981, which is where quantum computing was born. Significantly, the most important one here in terms of quantum computing is, he's up here, so with his arms folded, smiling. That's Richard Feynman, who you've probably heard of. He basically said, in order to solve the problems of quantum mechanics, so understanding how quarks and electrons and fermions and bosons, how these things interact and how they behave, those are combinatorial problems. They're calculating Hamiltonians and Lagrangians, so very energy functions of these actually quite simple systems back then. Just totally blew the computational requirements. And Feynman said, in order to model these systems, we're probably going to have to build a computer based on the same principles. That was kind of the birth of quantum computing. It was hosted by MIT and IBM. For me, and as an IBMer, if I look at that photograph, I see lots of young guys who are now IBM fellows, and lots of physicists who you've probably, if you've got anything to do with physics, you've probably heard of. This guy here, anybody know who that is? Anybody? Freeman Dyson. Yeah. So if you've never heard of Freeman Dyson, then afterwards go and Google him. And the other one, which the Germans all love, is the white-haired guy here, up here. This is Konrad Zuse. And Konrad Zuse, all the Germans say he invented the computer. Actually, he didn't. Charles Babbage, an Englishman, invented the computer, of course. So, another take on why quantum computing, just briefly. If we look at Moore's law and the growth of the computational power of classical computing, since I was a boy, and that started in 1961, and the first time I ever took a soldering iron in my hand was in 1968. So my father carefully guided my hand to assemble a small radio with transistors. We've seen a massive growth in the number of transistors and the size of chips. We've all heard of Moore's law. You know, the idea that I don't know how many transistors are in here. I mean, it's a 64 gigabyte memory. There's probably 100 gigatransistors in there or something. Back in the 60s, to even imagine that number of transistors and the computational power, even in my watch, for God's sake, would have blown your mind. One of the small problems with contemporary computing chips is that we're kind of, especially in feature size, we're getting to the limits of what at least classical silicon can do. The gate in a transistor is actually just a few tens of silicon atoms wide. And it no longer behaves like a nice on-off switch. It behaves like something which is sort of like an on-off switch, but not really. And we have to spend a lot of real estate on those chips to compensate for that. There are a few approaches to deal with that scalability. Going to 3D chips, going to neuromorphic chips, which is a whole other can of worms, so simulating neurons on a chip. Or, of course, to talk about quantum computing. This is the Oak Ridge National Laboratory Summit machine. You see all the wonderful numbers up there. Probably nowadays it's a big machine, and they actually have a connection to IBM's quantum computer. So they are exploring how to use quantum computing as almost like an accelerator. And in fact, that's one of the key challenges with quantum computing, aside from the fact that it's actually really difficult to get it to work. It's really difficult to get decent coherence times. It's very, very difficult to get decent error rates. The main challenge is how do you actually use that in problems today, to solve problems today. If we look at the history of quantum computing, so 1981, around then, that's when the idea of computers based on quantum mechanical principles was first formulated. We've seen a whole bunch of developments in the last 30, 40 years. Interestingly, if we look at 1994, not 1981, 1994, Shor's factoring algorithm. Anybody not heard of Shor's factoring algorithm? A few hands. Okay. This is the one that keeps all the cryptographers and security services awake at night. Kind of, theoretically, yes, it should keep them awake at night. Realistically, not yet. It's a long way away. Shor's algorithm basically takes something which we all use every day, every time I buy a tent on Amazon, which I do not every day. So you pay, and when you pay, you use SSL, and SSL is based on public key cryptography. And public key cryptography, most of it, but not all of it, is based on factoring large numbers. So finding out if a number is a prime number is actually quite easy. Finding out if a large number, which isn't a prime, what its factors are, is extremely hard. And that difference is what keeps public key cryptography secure. If we look at a 1024-bit key, which is pretty standard nowadays, then to crack that key using the Oak Ridge computer is going to take probably, estimate, longer than the time the universe has been around. 20 billion years to crack that key. With Shor's algorithm, using, let's say, the current clock rate, but that's the wrong word, it would theoretically take around 10 minutes. Now, that's an indication of what the power of quantum computing is. Actually, it's not a problem, because in order to do that, you're going to need millions or tens or hundreds of millions of qubits. We are currently, and by we I don't just mean IBM, I mean everybody apart from D-Wave, but they're doing something which is a little bit different than quantum computing. It's almost, but not quite quantum computing. If there's anybody from D-Wave in the audience, apologies, but we can talk. We can go outside afterwards and. So if you're using real quantum computing, then we're still a long way away from being able to crack RSA. But you get a feeling for where we are. The interesting thing about Shor's algorithm is that Peter Shor developed that without there having been any quantum computers around. So at that point, I don't know the exact figure, but I remember that I did my PhD in 82 to 85, and I remember I was 94, I was doing, around the end of the 80s, I was working on electronics research, and I remember vaguely some people talking about coherence times in the order of femtoseconds. Right now, the state of the art is maybe 100, maybe 150 microseconds coherence time. So every quantum computer program, every quantum program you write has to execute in maybe 100 microseconds, maybe a little bit more, maybe a little bit less. That's a constraint. Where can we use them? Well, this is where it gets interesting. Back when Richard Feynman and David Deutsch and all the other physicists, these guys were looking at using quantum computers to model physical systems, I guess the first use case or application area was physical systems. And what does that mean in the real world? That means actually chemistry. Chemistry, maybe biology, material science, that kind of thing. And why? Well, problems in those areas are very often about what shape is a molecule, what free energy does a particular molecule have, where is it going to bind to for example, where is an paracetamol molecule going to bind to human cell? Now, we all know, take paracetamol, it's a painkiller, it reduces fever. It's been out there for, I don't know how long has paracetamol been around. I think since 40s, 50s. Aspirin's been around even longer. It's a no-brainer. You don't really need to model them. We know how they work. But if you're developing new drugs, especially if you're developing bespoke drugs, individualized drugs, then that whole process of what works where, when, how, and why needs to be done a lot more quickly. Quantum computing isn't there yet, but that's a potential use case. Where it is being used in chemistry is in modeling simple molecules. And although it's quite trivial, that becomes, for example, quite interesting when you're talking about battery technology or modeling electrodes or electrolytes or new paint materials. So even with quite simple chemistry, it becomes interesting. Second area, it's actually the third on this list, is financial services, but actually anything to do with optimization. So it could be financial services, it could also be logistics. And there's a whole class of problems which we are looking at how to transfer those to quantum computers. I'll talk about how we do that in a second. The third area is generally in the area of artificial intelligence. That's the one with the biggest, let's say, question mark as to regards when, but also one of the biggest potential benefits. So three very active areas. The fourth area, of course, is cryptography, but nobody talks about that. So potential near-term applications. Yeah, you can see here a whole bunch of different application areas. Where are we right now? Well, back in the Solvay conference was somewhere here. The MIT conference was somewhere here. In 2016, we launched the Quantum Experience. The year afterwards, the IBM Q Network. In German, we have this lovely word, Mitbewerber. Is this something equivalent in Dutch? It's like a nice way of saying competitors. Competitors is kind of, you see, you don't have it in English. It's weird, isn't it? Mostly the English language is very, very good at expressing things with single words, but occasionally it falls over and the Germans are better. I know it's a Dutch audience, you're Dutch, so risky, but there you go. Okay, so where are we now? We, and by we I mean IBM, our competitors, and our customers, and lots of universities and startups and developers and yeah, everybody who's interested in quantum computing. We're all trying to understand where can you use this to obtain quantum advantage. There are a whole bunch of dimensions and implications about that. Starting with how do you integrate it with classical computing? You know, how do you put your quantum computer alongside your classical computer? How do you take classical algorithms, or can you take a classical algorithm, cut a bit of it out like a pizza, just slice the pizza out, replace that pizza slice with your quantum computer and make that much, much, much faster? Is that possible? There are certain cases where that works. Are there things which are amenable to be run purely on a quantum computer? How do you design algorithms generally to run on a quantum computer? There's all sorts of very, very interesting work going on. And in fact, if we look at the last 2 to 3 years, since IBM and Rigetti and D-Wave and others started to make quantum computers available, the number of scientific papers, the number of companies getting on board has really skyrocketed. Interestingly, I think it was your talk, one of your talks was the Chinese, the amount of money the Chinese are investing. It was yours, wasn't it? Yeah, and I seem to remember you said 220.
Yeah, that was 2015.
Yeah, put another 0. We don't really know what the Chinese are doing, but we know that they're investing big money in it. And we know that Alibaba withdrew their quantum computer, when was it? The fall of last year. A friend of mine developed a mapping for the Penny Lane software, for the machine learning software, which was back-end agnostic. And he wrote the back-end for the Alibaba machine, and one day later they pulled it offline. So he was a bit frustrated. So when we talk about quantum computing, we talk about universal quantum computing. That's kind of where we're all aiming for. But right now we are working with real NISQ, so error-prone, maybe fault-tolerant, limited number of qubits. And the challenge is how do you leverage that today? The third area is quantum annealing, which is kind of, it's like sort of overgeneralizing, but it's quantum computing without the entanglement, almost. When we talk about the power of quantum computers, we need to consider the number of qubits, but we also need to think about the error rate of the individual qubits, and actually that's far more important. For every percent in improvement in individual qubit error rate, that means you can effectively use like a lot more qubits in your calculations. So it's important to consider not just the number of qubits, but also the error rates, and of course the coherence time, the amount of time you have to run your program. So if you have 100 qubits and a 5% error rate, and your coherence time is 1 microsecond, I mean, yes, you can't really do anything with it. Quantum Experience was started in 2016. If you want to take a look at Quantum Experience, go outside. My colleague has it up and running on a computer. It basically implements music staff notation with simple, fundamental quantum operations. So Hadamard, X transformations, de Pauli operators, that sort of thing. It's free, at least on the 2 5-qubit machines, and I think on the 16-qubit machine. Although it doesn't work on the 16, it only works on the 5. 5 staves. Working with 16 staves is a little bit confusing. What we're also make available to the public, to you, is QuizKit, and that's where I wanted to spend a little bit more time talking about QuizKit. So QuizKit was actually launched last year. No, year before last. That's where I noticed that I'm getting old, because I teach at university, and I did a course in, what is it, it's 2019. At the end of 2017, I did a course at the University of Osnabrück, which is not so far from here, sort of to the east a bit. And it was on comparative or architectures for machine learning. And one option was neuromorphic computing, and the other one was quantum computing. And we used QuizKit version 0.3, I think it was. So it had just been launched. We're now much further, and there are various manifestations of QuizKit. QuizKit is an API. So for you as a user, it's either you either use it on a hosted Docker service, or you can use it native on your local machine through a typically a Python wrapper for a web service, or you can run it as a binder image. There are various options. Basically, you sign up with your LinkedIn or Google ID, or I think there are a couple of other options, or if you've got an IBM, you're an IBM customer, you've got an IBM ID. Basically use some kind of third-party authentication service, register, get your API key, you're up and running, and there's a whole bunch of tutorials and stuff. But QuizKit actually consists of different parts: Terra, Air, Aqua, and Ignis. So Aqua is water, Ignis is fire, Air is air, and Terra is earth. So somebody's watching, been watching Bruce Willis films, I think. Somebody got the joke. So it's all open source, Apache 2.0 license. Please go away, improve it, make it better. A couple of people already did, particularly one of the compiler components. Some Austrians did that. But being half German, I can't be complimentary about Austrians. That would be really... That would be like the Dutch being No, I can't do that either. What would it be like? Be like the Dutch being complimentary about who? Belgians. The Belgians. Belgians. Are there any Belgians here who are brave enough to admit it? Okay, guys, you know who to know afterwards, right? No one gets out alive. So what happens here? Okay, so QuizKit, open source library. QuizKit Terra. This is basically the level at which, or the simplest level at which you can program a quantum computer. It's a more or less an implementation of the Quasm quantum assembly language. Has anybody heard of Quasm? A couple of people. Okay. So Quasm is basically, it just says, here's a qubit, now do a rotation in, do a Z rotation in phase space, or do an X rotation, or do a Hadamard transform, or do a conditional knot entanglement, or some kind of basic gate level operation. So that's what Terra does to you. You install it on pip install QuizKit, and have a play around with it. That all works fine. Air. No, it's not a Canadian independent rock band. Or was it French? Are there any musicians here?
French group.
Was it? Yeah, I think it was right. So what do you play? Yeah, almost good. Any other musicians? Any real musicians? What do you play? The guy, what do you play? Did you put your hand up, the guy in black with the glasses? finally. Finally, a real musician. As a bassist to a bassist. Yeah, anyway, I don't know why I asked that. I was going to say something about bass strings resonating with each other, being like qubits and entanglement, but we'll leave that. Qiskit Aqua. Qiskit Aqua is actually the really kind of exciting part for users, because Qiskit Aqua allows you to use a quantum computer for real-world things. And I'm like totally over time, right?
You still have some minutes.
Yeah, okay. I just looked at my watch and went, Ignis, just been launched. Are there any physicists here? Any material scientists? Any electronics engineers? So if you want to play around with really the actual hardware and look at error rates and how temperature affects error rates, or you want to start experimenting with noise modulation, this is the API that you need for that. But if we go back very briefly to how do we use quantum computers to actually solve problems, this may have changed. As I say, there are scientific papers being published daily on how to develop algorithms for quantum computers. We have kind of 6 paradigms on how to use quantum computers. So things like the quantum Fourier transform, which if you're into electronics or signal processing it's a thing of beauty, of mathematical and conceptual beauty. It's really a very powerful tool. Quantum phase estimation, the variational quantum eigensolver here. So using the quantum computer to actually more or less physically model quantum systems on individual qubits. So there's like a toolbox full of tools for using quantum computers. And as I said, the number of scientific papers and the ways to use those techniques, actually quite powerful ways to use those techniques, is really very, very active area of research. Especially if we look at physics. So my favorite is caffeine. Caffeine has, I think, somewhere around 50 or 60 fermions. I think it's around that. You'd need 10 to the 48 bits of memory to model that system. 10 to the 48 is actually 10 to the 49, 10 to the 50 is the number of atoms in the planet Earth. So that's quite a big memory. I don't know if anybody's read The Hitchhiker's Guide to the Galaxy. Now you know the truth behind deep thought. Yeah, deep thought was actually a classical computer trying to model a quantum computer. If you've got any problems which are like these problems here, so traveling salesperson we heard about before, but DNA sequencing, arbitrage in financial modeling, integer programming, any kind of optimization. These problems are all equivalent to each other. They're all NP problems. So there's potentially quantum computing offers a way to drastically accelerate those. So I'm going to skip here because I've totally run out of time. No, I'm going to do this a different way. So, yeah, sorry about that. Yeah, this is an animated foil, which I'd forgotten about. Anyway, so relatively easy to install and use. And what you actually get is you have a GUI. You're able to see what's happening inside the quantum computer. You can either use a simulator or a real quantum computer. If you're using the real quantum computer, depends on the time of day, it might take a few minutes to actually come back with a result. Otherwise, yeah, pick another time of day. And basically it allows you to, for example, measure lithium hydride, beryllium hydride, simple molecules. There is also some work in there using support vector machines, matrix inversion using the HHL algorithm. So some very, very powerful methods to use a quantum computer at the level of what you see on the right. And is anybody here a computer programmer? Okay, so that was an encouragingly large number of hands. If you're programming Python, then you can use the quantum computer. So with those words, and given my penchant for just one final word on this baby. So we saw that, the system Q1. Why is it important? Well, because everything up to now has been research machines. So this represents, at least for IBM, the first step to providing quantum computing as a, let's say, a commercial offering. Why is that important? Well, it means that quantum computing is now taking its first tentative steps out of the research lab and into the real world where real problems need to get solved. It's a very, very exciting time, and as an IBM quantum computing ambassador, I'm right in the middle of it. It's a great honor to be there. If anybody wants to talk more, Stephanie's here, so she can help. Okay, with that, I'm gonna stop, because otherwise we'll be here all night. Okay, thank you.